Hello students, I am Dr. Navneet Kaur, Associate Professor in Department of Electronics and Communication, Sagar Institute of Research and Technology, Bhopal. Today I will be taking lecture on subject digital communication. The topic which I will be discussing in my lecture is Quadrature phase shift keying system. We have already done in our previous lecture that in binary phase shift keying, each symbol is represented by a single bit, whereas in quadrature phase shift keying, two successive bits in the data sequence are grouped together. This reduces the bit rate of signaling rate and hence reduces the bandwidth of the channel, which is an advantage of the system. In QPSK, two successive bits are combined. Thus, the combination of two bits forms four distinct symbols. When the symbol is changed to next symbol, the phase of the carrier is changed by 45 degrees. That's why it is known as quadrature phase shift keying. That means for each change in the symbol, there is a change in the phase of the carrier by 45 degrees. Now, this is the block diagram of QPSK transmitter. Here we can see BT, which is the bit stream, which is in the form of binary, either 1 or 0. Here, bit stream is given to two D-type flip-flop. One flip-flop is called even flip-flop and second is called odd flip-flop. For even and odd flip-flop, the clocks are generated by the toggle flip-flop. And this toggle flip-flop is generated by the clock frequency of FB. That means the period of the clock signal which is given to the toggle flip-flop is TB. Here we can see this is the clock signal and the time period of the clock signal is TB. So we can say the clock frequency is FB. Now this toggle flip-flop will act as a frequency divider. It will generate two outputs Q and Q bar. Q and Q bar are complement of each other. Q will be given as clock to the even type of D flip-flop and Q bar will be given as a clock to odd type of D flip-flop. So here we can see this is the even clock and this is the odd clock. And we can see that even and odd clocks are exactly complement of each other. Complement means when even clock is high, odd clock is low. And when odd clock is high, even clock is low. Now here, since toggle flip-flop act as frequency divider, we can see that here the time period of the clocks, even and odd clocks are now 2 TB. That means frequency is now FB by 2. Now, when clocks are given to these two D-type flip-flops, the outputs generated will be BET and BOT. The even flip-flop output is BET, that's why subscript E is used. And odd flip-flop output is BOT, O stands for odd. Now, BET and BOT, it modulates the two carriers cos omega naught t and sin omega naught t. Cos omega naught t and sin omega naught t are at 90-degree phase lag with respect to each other. Now, the output generated for first modulator is SCT, which will be BET into root PS cos omega naught t. And the output generated with the second modulator will be B naught t root PS sin omega naught t. So these two outputs will be added in the adder and the output generated will be the QPSK signal. So QPSK signal, which is represented by VMT, it will be SCT plus S naught t. SCT is BET root PS cos omega naught t plus B naught t root PS sin omega naught t, which is given in this expression. So here the flip-flop register alternate bits in bit stream BT and hold each bit for 2-bit intervals. So as I have already discussed in my block diagram, ST or VMT, which is the QPSK output, it is given by BET root PS cos omega naught t plus B naught t root PS sin omega naught t. So here we can see some important waveforms which can explain the working of the QPSK transmitter. This is the clock which is having a frequency of FB. When this clock was given to toggle flip-flop, the two outputs generated were odd clock and even clock, and here the time period is getting doubled. That means frequency is getting half. So here we have odd clock and even clock. Now odd clock is given to the odd flip-flop and even clock is given to the even flip-flop. Say this is the bit stream, which is the message signal. Now message signal can be in the form of 1 and 0. So here we have taken BT as 2 zeros, then 1, 0, then 111, then 00, and so on. Now outputs of the odd flip-flop will be B naught T, which will register odd number of bits. That means first bit, third bit, fifth bit, seventh bit, and so on. And BET, it will register even number of bit. That means second, fourth, sixth, eighth, and so on. So B naught T and BET will take alternate bits and will hold each bit for 2 TB. Now, representation of the quadrature phase shift king signal. Here we can see that we have two carriers, root PS cos omega naught t and root PS sin omega naught t. Cos omega naught t always leads sin omega naught t by 90 degrees. So we can see here, root PS cos omega naught t, it leads root PS sin omega naught t by 90 degrees. Now, since root PS sin omega naught t is in the downward direction, minus root PS sin omega naught t will be in the upward direction. Root PS cos omega naught t is in right direction, minus root PS cos omega naught t will be in the left direction. Now when B naught is equal to -1 and BE is equal to 1, then using this equation, by substituting B naught as -1 and BE as +1, we will get minus root PS sin omega naught t plus root BS cos omega naught t. That means we will take the negative direction of sine and positive direction of cos. So this is the positive direction of cos and this is the negative direction of sine. So when we want to find out the resultant of these two, since sine and cos are represented as vectors, we will get the resultant of these two vectors by using parallelogram law of addition. Now, according to the parallelogram law of addition, the resultant will be generated as the diagonal of this parallelogram, where its two sides is represented by root PS cos omega naught t and minus root PS sin omega naught t. So this will be the diagonal. So this point will represent B naught is equal to -1 and BE is equal to 1. And the length of this diagonal will be the resultant. So using the Pythagoras theorem, since this length is root PS and this length is also root PS, the amplitude, or we can say the length of this diagonal, will be root 2 PS. Similarly, when B naught is equal to -1 and B is equal to -1, then we have to consider for sin omega naught t and cos omega naught t the negative direction. So this is the negative direction of cos and this is the negative direction of sine. So this will be the resultant point. B naught is equal to -1, B is equal to -1, and here we can see the length of the diagonal is again root 2 PS. So the amplitude will be root 2 PS. Similarly, for B naught is equal to 1 and B is equal to -1, the point will be represented here, and the signal for B naught is equal to 1 and B is equal to 1, the signal will be represented here. So here we can see that the phase difference between two signals is 90 degrees. That means when signal is B naught is equal to -1 and B is equal to 1, and whenever there is a change in the symbol, there is a phase difference of 90 degree. Again, there is a phase difference of 90 degree. Now here I have shown it in the labeled form. Here we can see that the first signal is having phase of 45 degree with respect to the standard direction root PS cos omega naught t. But when we will consider the second symbol, now it is at the angle of 135 degree. So there is a phase change of 90 degree between two symbols. Now here we can see when two bits are 1 and 0, then with respect to the standard direction, the phase shift is pi by 4. Then when it is 0, 0, it is 3 pi by 4. When 0 and 1, it is 5 pi by 4. And when it is 1 and 1, it is 7 pi by 4. So here we can see, here the first even bits occurs after the first odd bit. So even number bit sequence starts with the delay of 1 bit period due to first odd bit. So there is always a offset between even and odd bit. This I can show with the help of waveform also. We can see that BET and B0T will never change its bit at the same time. That means if B0T will change the bit here, then BET will change the bit at this location. So there is an offset of TB. Again, if BET changes its bit here, B0T will change its bit after TB duration. So BET and B0T will never change its bit at the same time. There is always an offset of TB between BET and B0T. So this QPSK system is known as offset QPSK because here there is an offset of BET and B0T when they are changing their levels. This is all for today's lecture. Thank you.